Hey everybody, thank you for joining me. Today we are going to look at linear functions in context. So you're really going to use what we looked at in the first two lessons of Algebra 2. So remember that linear functions can be represented in a graph and an equation, in words, and in a table. So the agenda is to complete the do now. I'm going to ask you to work on the three examples. I have attached the Google documents. You may want to watch the video throughout your work and then submit the three documents and your Google Slides. So the do now asks you to write an equation in point slope form to model this situation, and you are given the number of text messages as the independent variable and the bill amount in dollars as the dependent variable. So remember, the independent variable is the X value, the domain, the input. The dependent variable is the Y value, the range, and the output. So the first thing that you want to do is to, and I apologize, this is from another course. So the first thing that you want to do is to find the slope. So to do that, you want to use the slope formula. And so you're going to take your change in your X value is a positive 5. And the change in your Y value is a plus 1. And I can see that is happening on each pair of points. As I increase 1 in my dollar amount, I'm increasing 5 text messages. So remember, slope is change in Y over change in X. So I have $1 for every 5 messages. And we like to represent that as a unit rate. So I'm going to divide 1 by 5 and I get 20 cents. So it's 20 cents per text message. So the first thing I want to do is write it in point slope form. And so all you need is a point. And we can take either of these points. And now we have our slope. So Y minus the Y I know is $26 equals the slope, which is 20 cents, parentheses X minus the X I know, which is 5 messages. Now from here, for number 2, I need to rewrite this in slope-intercept form. So point slope form is a right form because this form can be used for any situation, and it can be used to rewrite equations in standard form and in slope-intercept form. So we want to rewrite this in slope-intercept form, which is Y equals mx plus b. So I'm going to actually distribute in the equation above my 2/10 and then solve for y. So from here, I'm going to add 26 to both sides of the equation. And I get y equals 0.2 x plus 25. and that is part 2. So the next thing we're going to do is take a look at the next slide. One of the fundamental uses of algebra is to model the world around us. Algebra provides tools to translate a relationship we observe between two variables in an equation. We can then use the equation to make predictions or to analyze a situation. This activity is designed to help you learn to model linear relationships in real-life contexts. So there's 3 situations we're going to look at. One of them, the information is given in a context. You'll have an ordered pair. The second one, it's given in a table. And the third one in a graph. So I am going to ask you to complete each of the separate Google Docs that I've attached to today's lesson to show your work. And I made a little cheat sheet to remind you what the independent and dependent variables are, how to calculate the slope given 2 points, what the intercepts are, and then your 3 forms of linear equations: slope-intercept form, standard form, and the best form of all is the last form here, and it's point-slope form. All right, so let's look at our first situation. A biologist takes several measurements of concentration of contaminant in a lake after a chemical spill. After 4 hours, she measures 450 milligrams of contaminant per milliliter, and after 12 hours, the concentration has decreased to 60 milligrams per milliliter. So we need to answer these A through F questions and record our work. So at this point, what you want to do is go to the attached notes that I have given you, and you can see that you can type your work right here. So the first thing we want to do is define our variables. So our independent variable is time. And that's in hours. And our dependent variable sorry about the typo. Is the milligrams of contaminant. In milligrams. So we want to write the 2 points that were given. We can also write it in a table, but I'm just going to write the points. So 4 hours, 450 milligrams. And our second point is 12 hours, and we are down to 60 milligrams. So we can see that this is a negative slope just by looking at the ordered pairs, because the over time, as one variable increases, the second variable is decreasing. So we're going to write an algebraic model. So the first thing we want to do is calculate our slope. So I'm going to, at this point, erase all the other things that I had written down from the last slide. And I'm going to do the slope over here. So remember, it's m equals change in y over our change in x. So we have 450 minus 60 divided by 4 minus 12. So you'll need a calculator to complete this, and you need to take the difference of the numerator and the difference of the denominator and then divide them. So the difference in the numerator is 390, and the difference in the denominator is -8. So when I divide those, I'm going to get negative 48.75. Now, what does that mean? That's the milligrams per milliliter every hour. So it's decreasing 48.75 milligrams per milliliter. So to write a equation, I'm going to use point slope form. So remember y, and I'm going to use the first one. And slope is negative. And it doesn't tell me what form I need to write it in, so I'm going to leave it just like that. All right, so it asks us to interpret the meaning of the slope in the context of this situation. So what is happening is the amount of contaminants is decreasing 48.75 milligrams per milliliter every hour. And so the next thing, I'm going to write that in for part D, but to use our model to find out when there is no contaminants left, we're going to need to rewrite this in slope-intercept form and then solve for x when y is 0. So that's going to be a little bit of work over here on the right. So what I'm going to do is erase all this, and then we will actually interpret our meaning of our slope. And so the contaminant is decreasing 48.75 milligrams per milliliter every hour. All right, so to use our model, again, this is going to be a little bit of work. We're going to go back and we're going to distribute. So we're going to use this equation. And we're going to distribute the negative 48.75 and then add 450 to both sides. So remember, when you're multiplying a negative times a negative, you're going to have a positive. And that's 585. So now I'm going to add 450 to both sides of the equation. So my equation in slope-intercept form is right here. And I have to add the 585 and 450, so I get 1,035. And what I'm going to do is actually stop for a second. I'm going to record that right here so that we have it. So it says use the model to estimate the time at which there is no more contamination in the lake. So no more contamination would mean when y is 0. So I'm finding x comma 0, because remember the dependent variable is the contamination. So I'm going to sub in 0 here, and I'm going to solve for x, and that will give me the time. And so this is a nice two-step equation. Move this. So to solve this, I have to subtract 1,350 from both sides and then divide both sides of the equation by negative 48.5. And so I'm going to ask you to use a calculator on these, because the calculations would be really hard to do by hand. So that's step 1. And now step 2 is to divide both sides of the equation by negative 48.75. Okay. And that gives me 21.23 hours. So almost 21. And oops, let me erase that. And already here. So that's estimated about 21 hours, and we'll say quarter of an hour would be 15 minutes. And this is just an approximation. So at this point, we'd write about 21 hours and 15 minutes. Okay. So interpret the meaning of the y-intercept in the context of the situation. So it would take about 21 hours for the contaminations to be eliminated. So before there was, the concentration was down, of the contaminants was down to 0. So in other words, it will take over 21 hours for the contaminants to be eliminated from the lake. All right, so now I'm going to go back to our next scenario, and that next scenario, and again, this is the cheat sheet, so you might want to keep looking at this when you have some questions. So scenario 2, at AMATYC, an American Math Association of two-year colleges, generated this table to model the percentages of community colleges offering distant learning in recent years. Can this linear equation be used to model this data? Well, that is our first question, and we're going to take a look at that. And again, I just need to erase what we did in our last activity. So if it is a linear function, there is a constant rate of change. So I'm going to first look at the x's, which is increasing by 11. This one's 5.5. This one's 5.5. Oh, I'm sorry. This is our y values that we're looking at. And this one is 16.5. So we can see that change in y isn't the same, but we got to look at the change in x. This is 2 years. This is 1 year, this is 1 year, and this is 3 years. So if we take our change in y over change in x, if it's a constant rate of change, then yes, we can model this in a linear function. So I'm going to take 11 and divide it by 2. And that is the same as 5.5 divided by 1. And let's take our 16.5 and divide it by 3. And indeed, that also equals 5.5 divided by 1. So yes, we can model this with a linear function. So the next thing I'm going to do is go to our notes, and you're going to have to access that through the Google Classroom. So yes, there's a constant rate of change. So yes, we can model this with a linear function. Yes. Since there is a constant rate of change. Sorry about that. Okay, so our variables, the time in years, it's independent. I'm just going to call indie, and the percent of colleges in line is the dependent variable. Okay, so to find an algebraic model, we've got to do our find our slope, and then we can write this in point slope form. So we have our slope, it's 5.5, and so we can write this in point slope form. So if you remember, it's y minus the y you know, and I'm going to use point 1995, comma 33, and my m is 5.5. So y minus the y I know equals slope, which is 5.5, parentheses x minus the x I know. All right. So if we want to interpret the slope, so there is a 5.5% increase per year. And I believe that's it. Alrighty, so then the next thing we want to do is take a look at our last situation. So if we go back to our Google Slides, again, we want to take a look at our cheat sheet that can help us. And our last situation, corporations in the United States are doing quite well, thank you. The graph shows corporate profits in billions from 1988 through 2002, and we need to answer these different questions. Okay, so again, I built in the notes here. You're going to have to go into Google Slides and actually access it yourself so that you can submit it. All right, so interpret the 0.3, 520. So if we're going to interpret that 3 years, so 3 years after 1990, so in 1993, there will be $520 billion in profits. In profits. And again, I have some typos here. Thank goodness for spell check. Finality model shown in the graph clearly define the variables. Okay, so the nice thing about the graph is it gives us our x and our y intercepts. So first of all, time is the independent, the x value, x coordinate, profits. And remember, that's in billions of dollars. Y coordinate. Okay, so when we look at this graph, we can see right here, this is our y-intercept where it crosses the y-axis. And then to get our slope, we can just pick 2 points. And I'm going to pick 2 points that are really easy to read, here and here. So for our y, we're going increasing from 300 to, actually I can't really read that. So let me, the y-intercept, I'll rewrite it. So it's 0, 400 is the y-intercept. And our slope, we're going up 200 from 400 to 600. And remember, that's in billions of dollars. And over time, we went from 0 to 4. So that is 50 billion per year. So we have our slope and we have our y-intercept, and we can now substitute those in. And the equation would be y equals 50x plus 400. All right, and I'm going to write that right now. Okay, so what's the meaning of the slope? That means that every year the profits increase 50 billion. So each year, corporate profits increase $50 billion. clearly explain the meaning of the vertical intercept. That's your y-intercept. So in 1990, when this started, profits were, for corporate profits, were at 400 billion. So in 1990, corporate profits started at $400 billion. That's your initial value. Your y-intercept is your initial value. All right, so if we want to use our model to find the profit in 1998, well, that's 8 years since 1990. So x equals 8. So we're going to substitute in to our slope-intercept form 8. So we have 50 parentheses 8 plus 400. So I know that 50 times 8 is 400. So this would be y equals 400 plus 400, which is 800. So the answer would be $800 billion. Profits in 1998. And so I hope you found this video helpful. Again, the big idea is to look at linear functions in context, and we are using different representations, words and table and graph and points, to explain the key characteristics of linear functions and to make predictions, because really that's the point of algebra, to model our world and help us make sense of it. And in this case, I hope that you enjoyed these examples. Thank you for working so hard, and please submit your completed work. Good work. Thank you.